Okay, so last time we talked about some applications about why we have to worry about the forces that are acting on our bodies. Did not expect that to move. So now we have to begin thinking about, well, what is a force? What does a force do? So we're going to talk to someone who knows a lot about that. That's Sir Isaac Newton. And he had 3 laws of motion, which we're going to learn how to connect to force. So first off, a particle originally at rest, or moving in a straight line at constant velocity, will remain in this state. The resultant force acting on the particle is 0. Okay, so force is going to affect our velocity. Now I like to say that this is the reason that it's really hard to get up in the morning and really hard to go to bed at night. Because an object at rest wants to stay at rest. I don't want to get out of bed. An object in motion wants to stay in motion. I can't go to sleep. I've got so much to do. So, no, that's the reason it's so hard to go to bed. So the second law, if the resultant force on the particle is not 0, the particle experiences an acceleration. Okay, so resultant force not 0, we're going to have an acceleration in the same direction as the resultant force. This acceleration has a magnitude proportional to the resultant force. And finally, third law, mutual forces of action and reaction between 2 particles are equal, opposite, and collinear. So, an object in rest tends to stay at rest. An object in motion tends to stay at motion. Forces will cause acceleration, and for every action, there's an equal and opposite reaction. Now, the first and third laws were used in developing the concept of statics. You remember that. Everything had to be, some of the forces had to be equal to 0. Now, Newton's second law is how we're going to get dynamics into this class. Because we're bringing the fact that, well, our forces are not going to sum to 0, so some of the forces will not be equal to 0 in this class. No, that will not happen. And so there is going to be an acceleration. So F is our resultant unbalanced force. If it's balanced, it just means it's 0, and that means this will go to 0. By this class, it's almost never going to happen. And so we're going to have an acceleration, which will be a function of the force and the mass. Now, as a note, this is a simplification here. Most of these things you see are simplifications. Maybe you know about this equation where it's like energy is equal to 1/2 mass times velocity squared. That's a simplification. Actually, there's a whole bunch of orders of extra orders of magnitude that go along with it to make it much more accurate. It's just that for things that are moving slow compared to the speed of light, that's close enough. So when we get things that approach the speed of light, or if they're extremely small, this breaks down. It's not meant to be used there. We have to take in all those correcting terms. Now, some other forces we're going to have to worry about are like gravity. Gravity is going to be a big one for us. So Newton's law of gravitational attraction is simply we have this gravitational constant right here. And then we have m1 and m2. That's the mass of the 2 bodies. And then their distance separating them. So the closer you are to each other, the more gravitational force you will feel. The more massive they are, the more force you will feel. Now, this is not an equation that you're necessarily going to be very familiar with. However, you probably have heard about this one before. Weight equals mass times gravity. And what you've never thought about, though, is, well, what's that G? That G is all of this, just with numbers plugged in for Earth. So we plugged in the mass of Earth, we plugged in the average radius of Earth, and we went with it. What I also should tell you is that since the Earth is not a sphere, I'm very, very much exaggerating it. It does get wider around the axis that it spins around. Then gravity is actually less towards the equator because you are further away from things. And also depending on mountains and other crazy things, there are certain places where gravity is significantly less. It might be like 9.75 instead of 9.81. Okay, now here's a note. I mentioned this earlier. That, I wrote that equation, weight equals mass times gravity. And here's a mistake most people make. Mass and weight are not the same thing, okay? Mass is not equal to weight. Do not do that to yourself. Somebody in this class is going to see pounds and say, okay, that works. And then they're going to see kilograms and say, well, that's a weight too. It's not. In the United States, we typically measure everything in pounds, which is weight. In EU and all other countries, they measure things in kilograms, which is mass. Okay? So do not make the mistake. Kilograms, mass, pound force is weight. Okay, pound force is weight. Now, mass is actually really difficult to describe because it's an absolute property of a body, and it's just difficult to see it, like, color and other things, we can kind of take them with our eyes. Velocity, you can see how fast something is moving, but what about mass? What does it do? Well, if you want to measure mass, it's not just talking about weight, because your weight changes. Your weight changes when you're on a different planet. But the best way to describe mass is simply the resistance of a body to a change in velocity. If something does not want to change velocity, it wants to go at the speed it's going or stay stationary, then it has to be very, very massive. You realize this, like you can be in space, and here's this big asteroid which is coming to destroy the Earth. And there is no gravity around here, but if you take a little tiny dinky rocket and say, I want to push it out of the way, it's not going to work, because it's going to take a whole lot of force to be able to change the velocity of this giant mass. So we'll need a big rocket to push it back and save the planet. Okay, so mass is how difficult it is to change our velocity. Then what I said earlier, we get our weight from multiplying mass and gravity. And gravity is either 9.81 meters per second squared if your mass is in kilograms, or it is 32.2 feet per second squared if your mass is in slugs. Okay? Not pounds. Please, no, that's not how that force equation works. If you have something in pound force, it's already a weight. And if you see pound mass, then just remember that pound mass is the same as pound weight, pound force. It's a really weird one. So mass in slugs or mass in kilograms for this equation. Okay, so we'll stop there for today, and the next time we'll jump into some more fun stuff. So thanks for listening. I hope this helps you, and I'll see you all next time. Bye-bye.